We are currently live. Now the problem is the camera's on this one. If I look here, I'll have to look here. What should I say? Questions?
It's like 1 second behind.
Oh, you're on it?
Yeah.
All right. Now the next issue is there a way to share your screen? So let's just say I wanted to show something. You saw it on yours though? Interesting. Check, check, check. There's got to be a way to share your screen, right? I have no idea. Anybody out there has any questions? Let me know. Thanks. I appreciate it. Thanks for watching. So your comment about inference procedures. So it definitely could be a little bit tricky. So what I tell my students is just think about, is it proportions or is it means, right? So making that decision right there could help you. So just read the problem. Does it use percentages? Does it give fractions? Does it give 13 out of 22? Like that's going to be a proportion. And as it means, you're going to literally see the word means, or it'll also have quantitative numbers that have units. That's also a side of means. Then you got to ask yourself, am I working with one sample or am I looking at the difference of two samples? And that should be pretty obvious. Like, are there two samples in the problem? Is there only one sample? So when you go to that AP Stats formula sheet, on the back of it are two tables, one for proportions and one for means. And that'll kind of help you look. And then in each of those tables, there's a row for one sample, there's a row for two samples. So that can kind of help you determine which it is. Now, chi-square test is a little bit trickier, but chi-square test deals with tables of categorical data with multiple categories. So that's going to be a sign that you need a chi-square test. If there's only one categorical variable, that's a chi-square test for goodness of fit. If there's a two-way table for two categorical variables, you're looking at a either a homogeneity test or an independence test. So hopefully that helped you out there. All right, I was just reading the comments on my second computer. So somebody asked about how do you know if it's a two-tailed test? So anytime your alternative hypothesis uses a not equal to sign. So if the question does not specifically state that you're looking at the proportion being greater than 23% or less than 23%, or the mean being more or the mean being less, if it simply says we're looking for something different, meaning I don't care if it's more, I don't care if it's less, that's when your alternative would use a not equal to sign. And that is where you use a two-tailed test, because that means you don't care if you're on the top side or the bottom side. Either one is going to be fine to prove that it's not what you thought it was. And that is where you simply double your p-value at the end. So when you use normal CDF or TCDF to get your p-value, just double it at the end to make your conclusion. And I'll be honest, like, let's just say that there's an FRQ that incorporates that idea. If by accident you forget to double it and you were supposed to double it, but everything was correct, you're probably still going to get a perfect score of a 4, because there's so much going on in those problems. For them to take off because of that one thing is going to be very unlikely. So you'll still do pretty well. All right, how do you do a matched pairs test? That's a fantastic question. Literally, I have students in my classroom right now asking me about that one. I don't think I can share my screen, which I'm very new to this live chat thing, so I'm trying. But let me first find a question. So give me 1 minute to find a question, and I'll try to figure out if I could find a way to push it out to you guys or not. I don't know if I can be able to share my screen. If anybody knows how to share a screen in a YouTube live, let me know, and I'll do it. But let me get a problem first so we can do one. All right, so somebody asked about a match pair test. I'm going to do one. I have some students in my classroom right now. I'm going to do it. I'm going to try to possibly, I don't know if I'm going to be able to turn my camera so you can see the board as I talk to them about it. I apologize if it's going to be terrible quality, but this is the best I could do with the situation right now. If it doesn't come across very clear, I can talk to the camera a little bit closer after I help the students in my classroom. So I'm going to attempt to turn this around. This is not working very well. All right, I'm not going to be able to do that like I thought. All right, you can kind of see the board. Probably not going to be very great, but I'm still going to try that. All right, so I'm just going to make up an example real quick that will at least give you the idea, okay? So let's just say that we have two sets of data, and maybe it was one group of people. That's another indicator of a match pair test. One group of people, and we measured their weight before a new weightlifting program, and we measured their weight after, right? And I'm going to use a real small sample size of 5 people. So maybe the first person's weight before was 200 pounds. Their weight after is 195 pounds. Next person was 190 pounds before, 180 pounds after. Next person was 150 pounds before, 142 pounds after. Next person was 191 pounds before, 191 pounds after, so they didn't lose any weight. Next person was, let's see here, just make up something, 140 pounds before, 120 pounds after. Okay, so the first thing I do is like recognize that it's a match pairs test. It looks like I have 2 sets of data here, but the idea is that all I really care about is the differences because it's one group of people. So that's a big indicator is that read the problem, there's only one group of people. Right? So in this situation, all you really care about are the differences between the values. So if I look at the first person, they lost 5 pounds, 200 minus 195 is 5. Next person lost 10 pounds. Next person lost 8 pounds. Next person lost 0 pounds. And the next person lost 20 pounds. So that's the only list I really care about is the list of my differences. So obviously step 1, you're going to state that this is a one sample matched pairs test. And your null hypothesis is that the mean difference is equal to 0. So you're basically stating that, my weight training program didn't work at all. And then the alternative is that it did work and that the mean difference of weight lost is greater than 0. Okay, so you got to check your conditions, got to be random sample under 10% of the population. Now, 5 is actually not big enough. I just chose 5 to do this really quickly with you. So if this was 30 or more, then we'd be good. But I would have to look at my data and make sure there was no major skewness or no major outliers. And then a sample of only 5, it's not going to look very great at all, but just for sake of doing the problem, you get it right. Okay, now comes the work, which is actually really easy once you understand it. First, you do need to get the average difference of your sample. So you do need to go to your calculator, come up with the average of those differences and the standard deviation of those differences. Your calculator is going to do all that work for you. You have your calculator? So just make one list only of the differences. So 5, 10, 8, 0, 20. That's going to get me a mean and a standard deviation of the differences. For those watching at home, I'm terribly sorry that you can't see this. I threw this together at the last second. I can explain more detail if you want in a moment. All right, what'd you get, Rhea? 8.6 was the mean difference in standard deviation. That's the S. 7.4. Okay, so now all I need to do is understand that this is a one sample test, right? So I know it looked like two, but it's only one sample of differences. So I'm going to back of my formula sheet and I'm looking at one sample mean. That's going to have all the formulas I need. So first I'm going to need my t-score. My t-score is taking my observed difference of 8.6 minus the null of 0. I was assuming there was no difference whatsoever. And I need to divide by my standard error. Now, again, this is where you're going to go to your formula sheet, because on that formula sheet, there's a column for standard error. The standard error for a single sample is your standard deviation, which you said was 7.4, divided by the square root of your sample size, in this case, 5. That's going to give you the standard error for the denominator here. What'd you get? 3.31. Okay, so now we need to get our t-scores. So we're going to take 8.6 minus 0, which is obviously 8.6. Divide by 3.31 for our t-score. 2.599. Okay, so now for my p-value. The p-value is the probability that any other average difference is more extreme than mine. That's more than the 8.6 I got. That's going to be a t-score more than 2.599. Real quick, could be multiple choice question. Why are we using t and not z? Because the only standard deviation I have is that of my sample. I have no idea what the standard deviation of all people who use my training program would be. So now I'm going to go to TCDF on my calculator. I'm going to do 2.599 to 99 with 4 degrees of freedom, sample size minus 1. And that's going to give me my p-value. What'd you get? 0.0301. So that's one of those p-values where you have to either look at the significance level that they tell you or make up your own. So it could lead to 2 different answers. So if I use an alpha level of 0.05, I would reject the null. There is statistically significant evidence that using my training program will produce a mean difference greater than 0, showing that you will lose weight. Does that make sense? So it's pretty easy. Again, it's just recognizing it. The situations, there's 3 situations I've seen very popular when it comes to recognizing matched pair. 1, before and after. Like that's very common, right? That's very easy to see. 1 sample measured twice. That's matched pairs. Literally, the people are paired with themselves, their future selves and their past selves. Twins, the problem using twins, where we have a set of twins, each was measured. That's another great example of paired data. And then the other one that comes up very often was measuring something with 2 different measuring tools. A couple of years ago, there was a problem dealing with measuring E. coli in meat. They had 1 sample of meat. I think it was like 10 pieces of meat. They measured them with one method and they measured them with the second method. So again, it looked like there was 2 sets of data, method 1 and method 2, but it was really 1 sample that just got measured twice. Another example of a matched pair design.
So how come when you have like the problems that say firstborn and secondborn, that also is considered like matched pairs? Isn't it considered matched pairs?
Yes, that was another problem. Now that you're right, that wasn't what I just said, but those aren't twins, but they were still paired together because they have the same genetics, they have the same parents, they have the same home life. So you weren't necessarily twins, but you were the firstborn child and the secondborn child, but that still would make a great pair. I think that was a problem I made up. I don't know if that was a AP question. So I don't know if that means mine was better or not, but you get my point. Does that make sense for you? That help? Yeah, cool. And I've seen a match pair design question be on the AP test before FRQs. It's not common, but I've definitely seen it. But it's definitely multiple choice, where there'll be a scenario and you have to choose which type of inference is it? And if you recognize it as a pair, then you're going to choose it's a pair test. Okay. All right. Let me see if there's any other good questions out there. Some of you said you took it yesterday. I didn't know you could take it yesterday. You must be in a different country, would be my guess. Yes, they do make different tests for different time zones. So if you did take it yesterday in a foreign country, it's definitely going to be different. They have 3 versions of the test: international, A for United States, and then B for United States as well. So that's pretty typical. I don't see any other big questions here unless I'm missing something. If I missed the question, please don't ask it again. Okay, how do you do regression analysis? What do the standard errors on the chart mean? So on the formula sheet, on the back of the bottom of the back page, there is an entire box just for regression analysis. But usually you'll never need any of those formulas. Typically, if they're going to ask you a regression analysis problem, they're going to give you that computer output that shows you literally everything you need. You don't need to do any formulas at all. So the first column is for your intercept and your slope. The second column is for your standard errors. So there are formulas to generate those standard errors, but when you have that table, you don't need them at all. So the standard error that's next to the intercept is the standard error of the intercept. The standard error next to the slope is the standard error of the slope. And then you can actually conduct a test for regression analysis. I would need to show a lot more of that, but very rare for that ever to even be on the exam. But a test requires a t-score and a p-value. And if you follow that row, for example, the slope, you'll see there's a t-score there and there's a p-value there. So you guys should know that if there's a low p-value below 1%, then you're going to reject the null, which means that there is evidence that your slope is significant, meaning that the relationship between the two variables does in fact have a slope that would connect it together. So hopefully that's kind of a real rough review there, but hopefully that works. Brian said the multiple choice was hard. Well, hopefully that was the international one, and the United States one will be easy. Every year I have kids tell me the multiple choice is hard, and I have another group of kids that tell me it was easy. So, hard and easy is always in the eyes of the beholder. And somebody just said it was easy, but the FRQ was difficult. Okay. Somebody asked, how do you know what test procedure to use? I think I already addressed that, but I'll say it again if you're new to the chat. So you just have to kind of go through, is it means? Is it proportions? Are there 2 samples or are there 1 sample? Are they asking you to do an interval or are they asking you to do a test? Because all of that comes into play, right? So first, are you doing an interval or a test? That's going to kind of knock out half of the different inference procedures. Then is it proportion based? Like, does the problem deal with proportions? So that's going to knock out the formulas for means because you're clearly working with proportions. Then you have to ask yourself, is there just 1 sample or am I looking at the difference between 2 samples? And that's where you're going to look at that formula sheet. So the back of the formula sheet, there's a box for proportions, a box for means, and a box for slope regression. So that's where you got to make the decision. If I'm working with means, I'm going to go to that box for means, decide if it's 1 or 2. If it's for proportions, I'm going to go to that box for proportions, decide if it's 1 or 2. Is there a calculator shortcut test you can use for difference of means? Yes and no. There's not a direct separate shortcut just for difference of means, but you would treat it as you would a regular test for one mean, but you would need to know what those numbers represent. So you would just do a 1 sample t-test, but you know that what you're typing in is not the mean of a single sample, it's the mean of differences. So there's not a separate command for a paired test. You would use the exact same one because it really is. I mean, other than the concept of it, the formula and the procedures are exactly the same as a 1 sample t-test. Great question about how do I know when to use a t-test or z-test. So what I tell my students is like, just to keep it like, obviously there's a lot that goes into it, but just to keep it simple, if you're working with proportions, whether it be an interval or a test, you're going to use z. If you're working with means, whether it be an interval or a test, you're going to use t. Now, why t? Well, basically, anytime the standard deviation of your sample is the only standard deviation that you are given, that's what requires t. T model is I mean, for all intents and purposes, it's almost identical to the normal model, but it is slightly more accurate and slightly better when you are working with data that only contains the standard deviation of your sample, which means you have quantitative data. Proportions don't have quantitative data. Proportions come from categorical data, which is why proportions always use Z. You would never even think to use a T for proportions. But when you're working with means and you do not know the standard deviation of your population, you only know the standard deviation of your sample, that is when you're going to use a t-test or a t-interval. If for some reason a problem does tell you that you know the standard deviation of the population, then you could use a z-test for that problem. So one of my students just asked me about a goodness of fit test, specifically about the step 1 and step 4. So step 1, you're stating that it's a goodness of fit test. Now remember, a goodness of fit test means there's one categorical variable with many categories. Okay. So you would never use a goodness of fit test with a two-way table because that's two categorical variables. So your null would be that, obviously it's specific to a specific problem, but your null would sound something like the distribution of the categorical variable is the same. It is the way that we thought it was. It was what they said it was. Now, the same can mean 25%, 25%, 25%, 25%, or it could just mean the same as what we thought it was. Maybe that's 80, 10, 5, whatever. But it's just about, hey, whatever we thought was true is still true. The alternative would be that the distribution for that categorical variable is not what we thought it was. The distributions are different. Does that make sense? So then your p-value is either going to tell you to reject the null or fail to reject the null. So now that's your conclusion. So if you have a low p-value and you're going to conclude, okay, the alternative is true, I'm going to reject the null, then that's where you would say there is evidence that the distribution of my categorical variable, fill in the blank with context, is different than what we thought it was. Does that make sense? So that one problem we did with the moose, right? No one said that there's 25% of moose in the 4 regions. It was that the number of moose in each region was proportional to the acreage. But I can't remember what they were, like 31%, 20%, 25%, 19%, whatever they were. So you would just say, hey, the null would be that the proportion of moose living in each region is what we thought it was. It was proportional to the acreage. And then the alternative would be, it's not what we thought it was. Does that make sense? Cool. You want to get that door for me? Okay, let me see if there's any other good comments. Does your students watch your YouTube videos? They should all get 5s. So people are saying that you guys should all get 5s simply because you have me as your teacher. I will say this, the people that are in my room right now that came out of their own desire to study, I guarantee you guys all get 5s. I guarantee it's tough. I'll bet you $2 each. $2 each, you'll get 5s. Yes, sadly enough, no matter, I have students that don't watch the videos even though they should, but I do teach the stuff live, so hopefully they'll do well. How to use NCR in calculator for probability, somebody said. I said it real quick. So that's if you're trying to figure out like a binomial distribution. So you're going to go on your calculator. Try to show. See if I can show you real quick here. So you're going to go on your calculator. You're going to hit the math button. Well, actually, so first you have to type in your sample size. So maybe I have a sample size of 10. Then I'm going to go to math. I'm going to slide. It's probably see backwards. I'm going to go to slide to the PRB for probability and then go down to NCR. Then you're going to type in what you're looking for. So maybe I'm looking for 10 choose 2, which would mean I have 10 trials. And I'm looking for exactly 2 successes. So if I do 10 NCR 2, but again, you got to type in the 10 first, then hit enter, it gives you 45. So that's the first part to that binomial probability where you're saying, okay, there's 45 different ways this can happen. I need 2 of those to be successes. The other 8 would have to be failures. That's how that figure it out. So hopefully that explains. Are there simulations on the AP test? Boy, I hope not, because I didn't really go over that with my students. Simulations used to be a little bit bigger of a topic. They've kind of quite simply haven't addressed it in a lot recently. Like even on the past 3-4 years exams, I have not seen anything dealing with simulations. So unfortunately, I don't even teach it. I teach it, but not like that much in detail just because it's not on there a ton. So let's just hope it's not this year. Binomial versus geometric distribution, somebody asked about. Just keep in mind that they're both under the umbrella of discrete, meaning that the outcomes are whole numbers. Like the outcomes are whole numbers and that they're listable. Like you can make a list of the outcomes. Now, what differentiates them is both of them give you a probability of success. Like you have to know the probability of what you're looking for. So maybe you're shooting basketballs and the probability that you make a shot is 85%. Now, there's a couple rules with that. The probability of success must stay the same. You can't have a hot streak and get better or have a cold streak and get worse. It's got to stay 85%. The trials have to be independent of each other. And on each trial or each shot, you can only have two things happen. I either make it or I miss it. There can't be a third option like it just sits on top of the rim. Like that's not possible. So then what makes the difference between binomial or geometric? Binomial, you are given a set number of trials. Like you're said, hey, you're going to shoot 10 shots. And then the question is, how many can you make? I can make 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, or 0. That's what makes it binomial. I got the probability of success, 85%, and I have a set number of trials, 10. Geometric is there's no set number of trials. You're simply looking for your first success. The moment you get your first success, you're done. So you'd say, all right, what's the probability that my first success is the 5th shot? That means the first 4 are all failures. Like there's no other way that could happen. I miss, 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 and then the 5th shot I make. That would be geometric. So binomial, you're looking at how many out of n you are going to make, whereas geometric, you're just looking for your first make. So hopefully that explains it. Type 1 and type 2 error. So type 1 and type 2 error are again, theoretical. It's not like you're never going to be asked, did you make them, did you not? So type 1 error is when the null is true. So just keep that in mind. The null is true. So what's the error? You fail to, you reject it. Like you reject a false null. That's a type 1 error. So literally anytime your conclusion is to reject the null, there should always be a little bit of an inkling in your head of like, oh, maybe I'm wrong on this. Not that your math is wrong, that you actually did something that your data led you astray. And that could easily happen. Type 2 error is when the alternative is true, but you fail to reject the null. So you keep a false null, right? So the alternative is true. You should have rejected the null and gone with the alternative, but you did it. And again, it's all theoretical. So what can you do? Most of the time, what they're just simply going to ask you as a follow-up question is, hey, what type of error could you have made here? And if you rejected the null, there's a chance that the null was true and you weren't supposed to, and that would be a type 1 error. Anytime you fail to reject a null, there's a chance that you're making that type 2 error because maybe you were supposed to reject the null because the alternative was true. Now, power is the complete opposite of type 2 error, and that is when you do the right thing. The alternative is true, and your data helps you conclude that. That's where you have lots of power. All right, give me 1 second. I got to help a student. I'll be right back. All right, sorry guys, I'm trying to help everybody out here. All right, I'm new to this, so let's see other questions. Is a hypothesis test on a linear regression and slope likely this year? Listen, the probability, there you go. The probability of that coming up on any year is about 1% or less. I've literally only ever seen one FRQ that did that, and it was actually a number 6. So the probability of it happening again is very unlikely, but obviously it's not impossible. Somebody said, can we go over the important stats terms? That would be forever to do in the next couple of seconds. So I'm sorry. Without more specifics, it's hard to go over just everything. It's a z-test, but you only know the sample standard deviation. Okay, so somebody asked about t-test for z-test. Yes, like completely in general, 30 minutes before the test you're about to take, anytime you're working with proportions, you're going to use z. Anytime you're working with mean, you're going to use t. But the idea of why you're using t with means is because you only know the standard deviation of your sample. And that is when the t model is simply more accurate and better. That's why the t model was invented. You could use a z with means if you know the standard deviation of your population, which in most cases, you're never going to know that. So that's why. Most common probability screw-ups. Kids making up their own formulas that they've never been told or given. Like, keep it simple. Every formula you need is on that formula sheet. Don't try to do something that we've never, ever, ever taught you. How does degrees of freedom differ between each test? All right, I'll try my best to explain this because there's just so many options. But if it's a one sample mean, then it's just sample size minus 1. Easy for degrees of freedom. If it's 2 sample mean, then there's actually a couple options. There is an official degrees of formula for 2 sample mean, but it's very ugly, very complicated, and it's actually not required of you to use. So there's 2 options. I'm going to tell you what I tell my students. Use the smaller of the 2 degrees of freedom. So if you have a sample of 50 and a sample of 40, that means one has 49 degrees of freedom, one has 39 degrees of freedom. Use the smaller of the 2, which would be 39. The other option that teachers will tell you is add those 2 degrees of freedom together. So you'd add the 39 and you'd add the 49 to get your degrees of freedom. Both of those are acceptable on the AP exam, as well as the official degrees of freedom formula, which I would never recommend doing. It's a very complicated formula. I don't even show my students it. Now, when it comes to chi-squared, when you're doing a chi-squared goodness of fit test, it's not sample size minus 1, it's categories minus 1. So maybe you have a problem with 5 different colors, red, green, orange, yellow, blue. So you would do 5 categories minus 1, 4 degrees of freedom. If it's a 2-way table chi-squared test, then you're looking at categories minus 1 for your top variable, categories minus 1 for your other variable, and you're multiplying those together. So that was real quick run through on that. Sorry if that was complicated. Somebody said, when do you use degrees of freedom minus 2? Oh my gosh. That's the last place you would need degrees of freedom. I forgot about that one. Thanks for reminding me. When you are doing a interval or a test for slope, that is when it's sample size minus 2, because when you're working with slope, there are 2 variables, not just 1, and that's why you do sample size minus 2. So lots of different formulas there for degrees of freedom. I know that can get a little bit confusing. If you're doing a test, how do I get the p-value without the calculator? Again, I'm blanking in the linear regression t-test only using data sets. All right. Okay, in my opinion, the only other way, you need your calculator to get p-values. Like you have to use normal CDF or TCDF or chi-squared CDF if you're using the TI-84 calculators. But when it comes to another way to get p-values, you could use those tables, right? I don't know if your teachers show you those tables or not, but the Z tables and T tables essentially contain p-values if you know your Z-score and T-score. Those are for people who don't have access to a calculator, so I don't show that. And if you're referencing the shortcuts on the calculator, I personally don't like those shortcuts because you've got to show your work on the AP exam. And those shortcuts are basically just cheats. And to me, a cheat is cheating. So to get a p-value, you need your calculator and you have to know how to get your test statistic and then your p-value. So I don't know if that answers the question or not. I'm sorry if it doesn't. All right, what else here? What is the non-alternative test for slope? Okay, so your null would be that the slope equals 0. Now, if you have a slope of 0, that is a horizontal line that basically says that as one variable goes up, the other variable doesn't even care. It literally stays the same. So that's the idea, is that your null hypothesis is that these two variables aren't even related. One changes, the other doesn't even care. So your null would be that there is no slope whatsoever. That's a slope of 0. The alternative would be that there is a slope. Then you got to look at your data. Is it positive? Then you're going to say greater than 0. If your slope is negative, then you're going to go less than 0. That would be your non-alternative for slope. How long should I take on each question? Multiple choice, I would, you've got about a little over 2 minutes per question. But again, some questions are going to go faster. I would not spend more than 5 minutes on any multiple choice question. If you get stuck, just make a guess. FRQs, I usually tell kids, try to spend about, maybe 15 minutes initially on each question. So I tell students, just do the first 5. Don't even worry about number 6 until you're confident on the first 5. So if you do 15 minutes, you're already talking about, 15, 30, 45, there's an hour, you're at an hour and 15 minutes right there. So if you get 5 done in that amount of time, then that gives you about 15 minutes left to look at number 6. But some FRQs are going to be faster than that, way faster, and some may even be a little bit shorter. Mutually exclusive and independent events are literally two completely different. It means that 2 events cannot happen at the same time. And independence means that one variable or one event does not impact another. That makes sense. Would you use a t-test for means if you know the population standard deviation? No, I would use a z-test for means if you know the standard deviation of the population. But I've never seen an FRQ where they gave you the population standard deviation. Because if you think about it, a test is because you don't know the mean of the population. If you don't know the mean of the population, why would you ever know the standard deviation of the population? But to answer your question, yes, you could use a z-test if it was given. If you only get half of the multiple choice correct, what is the minimum score needed for FRQs? That's kind of a tough question, but it all depends what score you're looking for. If you're just trying to get a 3 to pass, well, if you get half of the multiple choice correct, you're looking at 25 points out of 100. You usually need around 45 to 50 points out of 100 to get at least a 3. So on the FRQs, you're looking for maybe half credit on every problem. Like, can you get 2 out of 4 points on every single FRQ? That'll probably do it for you. Or again, maybe you get like 2 questions fully correct and another question half correct, and maybe you get 0 on one question. So it's really kind of hit or miss. But if you just get around 50% of the multiple choice, 50% of the FRQs, you're probably going to get a passing score of a 3. Difference between matched pairs test and 2 sample test, that's a huge difference. So a matched pairs test is treated as a 1 sample test. The only thing you care about is the set of differences, which is only 1 set of differences. It's really about wording too. But anyway, a 2 sample test is when you're clearly looking at the difference between 2 separate samples taken from 2 separate populations, like students in Ohio versus students in California. Clearly 2 separate samples looking at the difference between them. Whereas a paired test is when you have data that is paired together, like using twins or having before and after, and you only care about the differences. But in either of those, you really only have 1 sample, which is why it's treated as a 1 sample test. We are 95% confident you will cry after the exam. Hey, at least it's over. Put a smile on your face for that. T-test versus Z-test. I think I've answered that a couple times. Sorry if you're new. But in very extreme general terms, Z-test is for any time you're working with proportions. T-test is any time you're working with means. But the reason why we use a t-test is because we only know the standard deviation of our sample, not the standard deviation of the population. Hopefully that makes sense. If you do know the standard deviation of your population, then you actually could use a z-test for means. Why don't we have to worry about that with proportions? Because proportions come from categorical data. There is no standard deviation of a proportion. A proportion is the proportion. You only have standard deviation when you're working with quantitative variable, which means you're working with means. Somebody said difference between homogeneity, goodness of fit, and association. So first, they're split into two categories. If you only have one variable and one variable only, maybe you have multiple categories, but one categorical variable, it has to be a goodness of fit test. If you have a two-way table that has two categorical variables, then it could be homogeneity or independence. The difference there now becomes how many samples were there. Was there one sample of people that you asked two questions, like what's your gender, what's your favorite color, right? That would be an independence test because you have one sample and you're looking at, hey, is there an association between gender and favorite color? Versus a homogeneity test is when you have separate samples. Like maybe you do a sample of people from middle school, a sample of kids from high school, and a sample of kids from college, and then you ask them another question for your second variable. But you clearly have three separate samples, and the test is looking at, is there a difference between those three groups of people, middle schoolers, high schoolers, and college students? That would be a test for homogeneity because homo means the same. So you're looking at, are things the same amongst these three samples, or are they different amongst those three samples? Whereas again, a test of independence comes from one sample that's just looked at twice. Hey, what's your gender? What's your eye color? Something like that. Goodness of fit test and homogeneity are not the same format. They're very different formats. I mean, they both involve chi-squared, which is the exact same formula, but the process of doing it, it would be better to say that an independence test and a homogeneity test, those are identical other than the name. The procedure is all the same. Goodness of fit test is only one variable, so it's a teeny bit different, usually less work. Yeah, I'll be right back. Okay. Somebody says, I don't think you're supposed to use a Z-score for normal CDF. Yes, you should be. Normal CDF comes from Z-scores. Now, if you're typing in your mean and standard deviation, then you actually don't need the Z-score, but I prefer to actually use the Z-scores. That is it when you leave your mean at 0 and your standard deviation at 1. In that case, you do need Z-scores. Somebody said, I don't feel like I know anything. I'm screwed on this test. Listen, just keep in mind, you get 50%, you get a 3, you pass. Easy, right? So you don't have to do well to actually do well. Keep that in mind. How do you remember the difference between type 1 and type 2 error? Okay, here's how I remember. So the null hypothesis is first, right? Like when you write your hypotheses, the null is first. So just remember, type 1 first, is when the null is true. So what's the error? Well, you rejected it. You weren't supposed to reject it. That's the error. The alternative is written second, so that's type 2 error. The alternative is true, but you failed to reject the null. So you don't go with the alternative when you should have. So that's how I remember them. Hopefully that helps. All right. Do you include outliers and box plots? Yes. In AP statistics, we made what are called modified box plots. Modified box plots show outliers. Your whisker then goes to the next highest or lowest value that's not an outlier. So let's say your highest value is 165 and you deem it an outlier, you're going to put a little asterisk there. And then your next highest value that wasn't an outlier is like 100. Your whisker would go to 100. The addition rule for probabilities. So that is to find the probability of A or B. It's the probability of A plus the probability of B minus the probability of A and B. Now, why you subtract A and B is because the probability of A and B is incorporated in A. Because when you just talk about the probability of A, some of it is B. When you talk about the probability of B, some of it might be A. So if you just add A and B together, you're actually double counting the A and B. That's the overlap, which is why you want to subtract it away. So you're subtracting it away not to get rid of the and, but to stop it from being double counted. Hopefully that makes sense. I wish I could share my screen. I have no idea how to share my screen with YouTube Live. I'm working on it. That way I could actually show you guys stuff, but I'm sorry. If anybody knows how to, please let me know. How do you calculate expected values on the TI-84 calculator? Okay, so in list 1, you're going to put your outcomes. Like maybe the number of t-shirts I sell is 0, 1, 2, 3, 4, 5. So that's list 1. The probabilities go in list 2. So you put the appropriate probabilities right next to them in list 2. Make sure they correspond. So the probability of 0 t-shirts goes next to 0 and so forth. Then on your calculator, I'm going to try to show you, but I think it ends up being mirrored backwards. You hit stat, go over to calc, and choose one variable stats. Now, list is going to be your list of outcomes, which I just said was in list 1. So under list, you're going to put list 1. Then you're going to put list 2 as the frequency list underneath that, because the frequencies are what are attached to those outcomes. So you got to tell your calculator that. Then when you hit calculator, the expected value is at the very, very top. It's the mean. And then your standard deviation is there as well. So that's it. Pretty simple. Let's see here. Yes, to do the expected value mean by hand, it actually is pretty easy. You take each outcome times its probability and then add all those together and you'll get your expected value pretty quickly. Most kids can do that faster rather than actually going through the calculator process. But for standard deviation, calculator is going to be a lot faster. No, sorry, I had it on mute. I was helping a student. I apologize. That's why it was on mute. Is there a shape of box plots? Yes, yes. The only thing with box plots is you really can't see gaps in the data. But if you have a box plot, I could try to show one real quick here. I wish I knew how to share my screen. I apologize. So if you had a box plot that looks like this, like that's clearly skewed, right? You have a very low spread over here and a very large spread over here. That's going to be skewed. Versus if you have a box plot that looks more like this bottom one here, it's very symmetric, right? The left side and the right side are pretty evenly balanced. The median is right in the middle. That's going to be a nice symmetric one. So you can also see that. You're not going to be able to see like bimodal or gaps. You won't see it in a box plot, but you can see roughly skewed left, skewed right, and symmetric. How do you figure out the power? Not in the AP curriculum. You will never be asked to actually calculate power. The only thing they will ask you is how do you get more power, which there's three things. Number one, bigger sample size. Bigger sample size is always more accurate. And if you are wanting to reject the null and go with the alternative, a bigger sample will reveal that easier. The second way is to increase your level of significance, alpha. So if you go from an alpha of 1% to 5% to maybe 10%, you are giving yourself more power because what you're doing is you're opening up the door for more rejection. If I use an alpha of 10%, that means I'm way more likely to reject, but that's what I'm supposed to do, right? Because that's power, is rejecting when you're supposed to reject. So increasing alpha gives you more power. And the last way is if the truth is further from the null. Let me try to explain that. So if your null hypothesis is that the mean is 10 and the truth is 12, well, 12 is only a little bit bigger than 10. You might not necessarily see that in a sample, hence make an error. But if the truth is 47, way more than 10, well, then you're clearly going to have more power because if the truth is 47, samples should be near that truth. And that means you're going to be way far from 10, and hence you're going to reject the null. So hopefully that made sense. It's not covered in the College Board videos. Yeah, hopefully you're talking about power there. Yeah, because you don't actually have to calculate power. You just need to understand what it is. Inference with regression. I mean, at this point, an hour before the test, I would say just don't worry about it. Usually you're talking about 1 to maybe 2 questions on the exam. So sorry. A matched pairs test is when you're looking at one set of data that was measured twice. So it may look like you have 2 sets of data. So most kids might interpret that as 2 samples, but no, read the question. Maybe you have 25 people, one group of 25 people, and you measure their weights before an athletic program and after an athletic program, and your goal is to see if they lost weight. Well, it's going to look like you have 2 sets of data, but you actually don't care about the 2 sets. You only care about the differences because there's only one sample. It's really in the question of the wording, right? A 2-sample test will be like, is there a difference in is there a difference in the means of these populations, right? So if you're looking at the difference of the mean of guys versus the mean of girls, you clearly have 2 samples, one of guys, one of girls. Whereas a difference of means is more about, hey, is there a mean difference? Meaning, is there an average difference between what happened here and what happened here? So hopefully that kind of makes sense. Using twins oftentimes generates a matched pair design or doing one, anytime you're measuring something twice, one group of people measured twice or one group of objects measured twice, that's another example of a matched pair design. What are the predicted FRQs? So I'm going to tell you right now, there's going to be 1 over exploring data, which is looking at a histogram, a dot plot, or a box plot. There's going to be 1 over inference. There's just a lot of different types of inference. I can't tell you which one. There's going to be 1 over collected data or experimental design, and there's going to be 1 over probability for sure. The other 2 are probably going to be on more of those topics, maybe regression, but it's not going to be a test for regression. I promise you that, at least I cross my fingers. But it's probably going to be like maybe they give you a scatter plot and they just ask you to describe it. They ask you about slope. They ask you to interpret slope, but they're probably extremely unlikely. It's like p-value, right? I would be shocked if it happened if they asked you to do a test for slope in an FRQ. Oh, boy. I'm sorry. Some people are saying that they're so confused. I'm sorry. Not that I could do about it. Can I do probability? That's way too vague to answer with just a couple of little bit time left here. We need a little bit more specifics. I do have a probability review video. It's 45 minutes long. Watch it on double speed. Maybe you can get it in time. It's called Ultimate Review for Probability. It really covers everything. Oh, boy. When a test is asking for the difference between like two means, do I like subtract the means and standard deviation? I'm trying to understand that question a little bit better. If you are doing a test for the difference between two population means, you subtract your means. Yes, that is your observed difference. But for standard deviation, you do not subtract means, or you do not subtract standard deviation. Remember, you're only allowed to add variance. So variance always adds. So that's why you got to use those formulas on the formula sheet. They actually show you all the work for you. All right, so one of my students just asked me, if you were asked to describe a scatter plot, what do you say? So I'd mentioned four things: shape, direction, form, and, well, that's shape. Hold on, let me restart. Direction, let's start there. Positive or negative? Or is the scatter plot going up or is the scatter plot going down? As X goes up, does Y go up? Does Y go down? Positive, negative. Form, you're saying, like, does it make a line? Does it make a curve? Does it make a parabola? Hopefully it makes a line because that's what we like in stats class. And then we have strength. How closely do the points make that form? So if it clearly is making a curve, you're going to say it's pretty strong. If it's clearly making a line, you're going to say it's pretty strong. Otherwise, you'd say it's kind of weak. And then the last thing is give a context statement. Hey, as the X goes up, the Y goes up. One of the examples, just I remember off the top of my head, is as the distance a house is from the center of the city goes up, the price of the house goes down. So there is my statement in context. Now, in terms of correlation, remember, correlation measures the strength, the direction of a linear relationship between two quantitative variables. So if they're not quantitative variables, if one of them is categorical, and you can't even make a scatter plot, don't use the word correlation whatsoever. And we don't ever use correlation if we're not linear. So you might have a giant curve in your data and it might be very strong, but we would never use correlation R to talk about it. And then it also measures strength because remember, correlation starts at -1 and goes to +1. The closer you are to -1 or 1, the stronger the relationship. The closer you are to 0, the weaker.
So 0 would just be like points all over the place?
0 would be two things. It'd be points all over the place, like a swarm of bees, or a parabola. Why? Because a parabola is half positive, half negative. That's why we give a correlation of 0. One second. The other reason, but think about it, if you have a parabola, you would never use correlation in the first place because of what I already said, that correlation is only for linear data. Now, there is a formula for correlation. It's on the AP Stats formula sheet. You'll never use it. Correlation will usually be given to you. If it's not, what will be given to you is R squared. So all you got to do is take the square root to get your R. Does that make sense? You can also use your calculator to get correlation, but usually they're not going to have you do that either. They're going to just give it to you. Or they'll give you R squared, which means you got to take the square root of it. R squared tells you the proportion of variance in the Y variable that's actually because of the variation in the X variable. Yes. So you'd say, hey, 76% of the variation in my Y variable is actually because of the variation in my X variable, showing you how connected they are. Cool. Let's see here. I'm trying to keep up with all the questions. I'm sorry. Can you combine standard deviation by squaring them and taking the square root? Absolutely. Yes. That is how you combine standard deviation. You're not allowed to combine standard deviation, so you have to square them first. That creates variance. Literally taking standard deviation, squaring it, boom, you got variance. Add your variance, they never subtract, and then put a giant square root around all of that. That's how you get your combined standard deviation. Type 1 correctly. What's the difference between type 1 and type 2? Okay, give me a second. I got some students that need help. All right, so real quick, type 1, type 2 error. Type 1 error, the null is true. The error is that we reject it. So anytime you reject a null, there is a chance to make a type 1 error. Type 2 error, the alternative is true. The error is you kept the null. You failed to reject the null. So you should have went with the alternative, but you didn't. So that's the difference there. Hopefully that was a quick explanation. How good do we need to get a 4? Usually around it's tough, but usually around 55% to a 60%. All depends. Every year changes. Usually 65 to 70% is a 5. And then, maybe 55 to 65 is a 4. It all depends, but somewhere around there. Somebody wrote 50 something, I think. In some years, 50 could get you a 4. Again, it really all depends. A 50% is kind of borderline between a 3 and a 4. Okay, can you explain pooled data? Okay, so pooled is an older term. The AP Stats actually calls it combining now. It's the same thing. Pool is just putting them together. Combining, same thing, putting them together, right? So that is when you have a 2 sample Z test. Technically, the null is that the 2 proportions are equal. So if the 2 proportions are equal, the idea is, why do we have 2 separate samples then if they're all equal, right? So that is how we create our standard error combined. Your standard error pooled, maybe your teacher told you. Now, first off, pooling is only to create standard error. You don't use it for anything else. So what you do is you take all of your successes in your numerator, both samples add together in your denominator to get you one total p hat pooled or p hat combined, one total sample proportion, everything put together. Then when you use the standard error formula, that's the value you're using, right? And you're going to use it for both samples, right? So if you look on your AP Stats formula sheet, on the back page, there's a box for proportions. There's a row for 2 proportions. In that standard error of that row for 2 proportions, at the top is the generic standard error that you would use for an interval where you're keeping them separate, p hat 1 versus p hat 2. But underneath that is, hey, what do you do if p hat 1 equals p hat 2 or p1 equals p2, meaning your null, right? Your null is that they're the same. And that is when you follow that combining procedure, which is explained in that little bottom section of the box there. So I hope I briefly went over that very quickly. Now, here's good news, right? I tell my students all the time. If you forget to pool, if you forget to combine in a 2-sample test, you will actually not lose any points. If everything is correct and you do standard error and you don't pool them, you keep them separate, you will still get full credit as long as everything is correct.
I heard you talking about combine or something like.
Quick review of power, and that's it. Then I got to go. My students are getting ready to leave. So power is doing the right thing. It is the probability that you reject a null that is wrong and you accept an alternative that is correct. That's power. Don't ever worry about calculating power. Just understand the concept of it. And there's 2 really good ways to get power. Bigger sample size and increase your alpha value. That'll give you more room to reject. And if you're supposed to reject, that's what you should be doing. All right. I love you guys very much. Thank you for watching. And I appreciate you guys chiming in. I threw this live review session together at the last second. It probably was terrible, but if anybody learned a little bit, good for you. Thank you guys very much for paying attention. See you later.